Welcome back. So in our last class, we learned about the idea of image formation, and we found out how to use ray tracing to sketch what is happening in spherical mirrors. What we ended on last time was that we found out that the magnification of an image was equal to the negative of the distance of the image divided by the distance of the object. So the distance of the object is always positive in mirrors, and the image distance is positive if it's on the same side of the mirror, and if it's negative if the image is virtual and on the opposite side of the mirror. This also means that if the magnification is negative, then the image is inverted on the same side of the mirror as the object, and if it is upright, then it's virtual. The way we figured this out was by using ray tracing, and we drew a ray of light that traveled from the object, reflected off the center of the mirror, and then bounced through the image. So by drawing these two triangles, we could see that the two triangles were proportional to each other, so we could find their relationship. Next, we want to use ray tracing to find a more general way of figuring out where the image will be formed. In this case, we have our image and our object, and we draw a C-ray that goes from the object and then through the image and finally reflects off of our mirror. The key thing to notice is that the triangle created by the distance from the object to the center point and the triangle made by drawing from the center point to the image, they are the same triangle. By recognizing that these triangles are proportional, we find out that the radius of the sphere plus the distance to the object divided by the radius of the sphere minus the distance of the image is the same proportionality as the distance to the object divided by the distance to the image. So from there, we have some algebra to do, but when we're done, we find out that the radius divided by the distance to the object plus the radius divided by the distance to the image is equal to 2. If you remember, the focal point is 1/2 the radius of the sphere, so the final form of our mirror equation is 1 divided by the distance to the image plus 1 divided by the distance to the object is equal to 1 over the focal distance. So this equation is very useful if you're trying to figure out the magnification, because if you know where the object is and you know the focal length, then you can find the distance to the image, and if you know the distance to the image, then you know the magnification. And if you also know whether the image is inverted or upright. So yeah, it's very powerful to use the mirror equation. In order to use the mirror equation, we have to be very careful about the signs of our values. So for mirrors, the sign can be figured out whether the item we are interested in is in front of the mirror or behind the mirror. So for focal length, for concave mirrors, the focal point is in front of the mirror. So it's like the satellite dish where you're focusing your radio waves. So, and for a convex mirror, the focal point is behind the mirror. So the focal point is negative for a convex mirror, and it's positive for a concave mirror. For the image distance, if the image is in front of the mirror, it's positive again, and if it's a real image, then it's positive. And if the distance to the image is negative, that means that the image appears behind the mirror. So for a magnification, when m is positive, the image is upright, and when the magnification is negative, then the image is upside down. So for a single mirror, upright images are virtual and inverted images are real, but if you do have multiple mirrors, then you can change this, so you have to be a little bit careful about that. So for object distance, in front of the mirror, so it's a real object is positive, and behind the mirror is negative. So again, for single mirrors, your object is always going to be in front of the mirror. So with this, right, if you have a single mirror, but I suppose if you have multiple mirrors, then you can create a situation where a image is virtual then. Okay, so you're going to have to do a little bit of algebra, but basically on your next questions, you're going to use the mirror equation to solve for the focal point if you know the position of the image and the object. So there, you can pretty much use your mirror equation here, and you shouldn't have too much trouble. All right, so good luck, and then next we're going to work through these examples using concave mirrors and then looking at convex mirrors.